So for a quick executive summary, we've conducted research into adding quality constraints to the assembly job shop scheduling problem, a variant of the popular combinatorial optimization problem where we assign assembly operations to machines in a manufacturing scenario. We use genetic programming to model the part quality transformations, where the quality attributes of the subassemblies contribute to the quality attributes of the final part. To optimize this system with the new constraints, we developed a custom genotype and use NSGA-II to optimize across multiple objectives. We're going to start out with the problem motivation and some context about this project. This project was conducted at a trusted foundry. At a facility, we produce a small quantity of parts, but they have very strict quality requirements. Due to this, these parts are often inspected during each stage of assembly to reduce the number of failed parts. Our facility's primary objectives are make span, the time it takes to complete an order of parts, the overall part quality, and the first production unit, as our customers like to have an early unit to inspect. As such, the goals of this project were to first find a way to capitalize on the intermediate inspection data that our facility had been collecting, and second, to build tools which may be useful to plant schedulers and administrators to augment the existing ERP tools that they had been using. Moving on, we'll now talk about the methods we use to model the part quality transformations. To test and verify our part quality models, we conducted experiments on 70 instances of a single part and its subparts. Since this was real-world data, holes in the inspection results were replaced with zeros. To perform the modeling, we used COSA-style genetic programming with the variables assigned to the part quality attributes of the subparts. Each quality attribute in a produced part is assigned an individual tree. With genetic programming, we were able to achieve a 95% accuracy using the fitness formula on the right, with alpha being the correct value and beta being the model's value. Therefore, we can conclude that it's possible to effectively model some of the part transformations with genetic programming. We will now cover some background about the assembly job shop scheduling problem. The AJSSP has two primary components, the first of which is this part dependency graph, which describes what subparts combine together to create parts. As we can see in this example, P4 and P5 combine to create P2, and so on and so forth. With this dependency graph, we can begin assigning jobs to machines in the factory. As we can see, the subparts, like P1 and P2, have to be assembled before the final part, P0, can be produced. And as such, it's possible to produce invalid schedules. In this example, P4 is only produced once, which means that P2 cannot be produced, which means that P0 cannot be produced. We should also note here that it's possible to overproduce the number of subparts ahead of time and store them for later usage. With this work, we added quality constraints to the problem. Each part has quality attributes. During assembly operations, the transformation models, as shown before, are used to calculate the produced parts quality. For the base parts, the parts with no children, we simulate suppliers, which provide large quantities of parts of varying part quality. Finally, we add quality constraints to the final part, or the deliverable part. They can only be accepted if they meet certain quality thresholds. Now we'll move into the custom genotype for the AJSSP problem with quality constraints. Our genotype is made up of two components. The first is a schedule which describes the order that parts are produced. The second is what we're calling part rankers, which describe what parts to use in assembly operations. These are COSA-style genetic programming trees that are similar to the part models. They use part quality attributes as the variables. During an assembly operation, first the schedule is used to determine which part is to be assembled. Next, if there are multiple subparts, the respective part ranker calculates values for each part. The subpart with the highest value is selected for assembly. There are two things of note about our mutation and recombination operators. First, schedules are initialized, mutated, and recombined iteratively to guarantee that no invalid schedules can be produced. Second, since our genotype contains two different components, they can be mutated and recombined in a variety of ways. During these operations, a special strategy parameter controls if one or both elements get modified. We'll now talk about our experiments and results that were conducted with the quality constraints and optimization method. For our experiments, we ran on semi-randomly generated part models with a 3-stage assembly process. The full details are described in our paper. In the factory, we used 3 different machines, but each machine can only assemble a certain subset of parts, so they must be carefully coordinated. Following our facility's primary objectives, we chose to optimize make span, part quality, and the first production unit. We compared, using our genotype, 3 different optimization algorithms: evolution with NSGA-II, random search, and a multi-objective hill climber. Taking a look at our results, on top we have our relative performance results. These were generated by analyzing the Pareto fronts of the different algorithms. Each algorithm was run 30 times, so each row has 900 comparisons. If one run dominated the other, it was noted, and if not, it was considered a tie. When 2 runs tie, their Pareto fronts are combined. The run that contributed more to the final Pareto front is assigned a greater tie. As we can see, evolution is significantly better than the other algorithms. In the bottom graph, we are looking at the average front sizes and objective ranges. These are various metrics which we think may be useful to schedulers. With high ranges and large Pareto fronts, schedulers would have a lot of diverse options to choose from. Evolution and random search produce the highest range of solutions. Looking at our raw performance results, it confirms our previously shown relative performance results. Evolution was able to find significantly better objectives, especially in make span and part quality. From our project, there are 3 main takeaways. First, we've shown that genetic programming is capable of modeling part transformations during the assembly process using real-world data. Secondly, the AJSSP is a problem that part quality can be integrated smoothly into. The constraints and objectives naturally mesh with the existing constraints of the AJSSP. Finally, with our genotype, we've demonstrated that evolution is more efficient at finding effective solutions than random search and hill climbing. As this is still an early work, there are many different directions which it could be extended. First, we conducted some experiments with multiple part lines, but they were not very successful due to Pareto front explosion. NSGA-III and other many objective optimization methods may be suitable for larger optimizations. Using these new constraints, we could evaluate the effect of attacks on various factory and supplier components. These could include impacting the quality of the supplied parts and seeing how that affects the output parts. Competitive coevolution may be a potential optimization method to evolve both the attacking and defensive sides of this problem. Finally, since we have 2 separate components in our genotype, cooperative coevolution may serve as an alternative optimization method which may be more efficient than our current modified mutation and recombination methods. That's it for the presentation. Do we have any questions?